Okay, so we're looking at still looking at problem set 1. These are problems 5 and 6. They're two first order systems. One's mechanical, one's electrical, and I purposely designed these to show the similarity, that analog between mechanical and electrical systems. So the first one here is a mass sliding on a flat surface with an oil film. So it's a mass and a damper. And it becomes a first order system in velocity, so that we're asking you to write the differential equation that relates the velocity to the applied force, and given the initial condition of 0 velocity, and the applied force has a step change to a level of 5 newtons, solve the differential equation. So let's go over to my solution here. I write the free body diagram, very simple. There's our applied force. Here's the resisting damping force. Newton's law says m times the derivative of the velocity is equal to F minus F sub b. That resisting force F sub b is b times velocity, right? B was given as the coefficient of damping. So the differential equation is very simple. mv dot plus bv equals F. So first order, non-homogeneous because it's got a forcing function. We know the value of the forcing function, it's 5. So the form of the particular solution is just a constant, right? This is a 0th order polynomial. We only need one term. Its derivative is 0, so plugging that back into the differential equation, we come up with the answer that A, the particular solution, is 1/5. We move on now to the homogeneous solution, and we jump right to the characteristic equation. M times d plus b equals 0. That gives us a root of -1/4. And that directly leads to the form of the homogeneous solution to be some constant of integration, c1 is equal to exponential of minus t over 4. And combining that with the particular solution gives us this total solution of c1 e to the minus t over 4 plus 1/5. And finally we apply the initial conditions, that at t equals 0 that total solution has to also be 0, which leads us to the conclusion that that constant has to be -1/5. So the total solution can be written in this form: 1/5 times the quantity 1 minus e to the minus t over 4. This form, some of you may recognize, as the classic solution to a first order system with a step input. It's called the step response, and it has certain characteristics that are defined by the exponential, by the root of the characteristic equation, also known as the time constant. So 1 over the root is the time constant. So the root was 1/4, so the time constant here is 4. We're going to talk more about that in the coming weeks, but I wanted to sort of let you think about that for a minute. Okay, so that's problem 5. Pretty straightforward, hopefully. Hopefully didn't cause too many concerns. Problem 6 now is an electrical system with a resistor and a capacitor in series. And the output, the thing we're interested in, is the voltage across the capacitor. Okay, so write the differential equation and then solve it for these conditions. So let's say in this case the applied voltage has been 5 volts for a long time, meaning there's no transients, it's reached steady state. That means there's no current, so that means if this voltage is 5 volts, then this voltage is also 5 volts. And at t equals 0, we suddenly change the output to 10 volts. Now we want to find the function that describes that. So the way to interpret that is the initial condition for that capacitor, the voltage across the capacitor, is 5, right? So what I'm trying to get you to be thinking about here is not just how to solve a homework problem, but how to take a physical reality and turn it into the form we're used to seeing as a homework problem. Okay, so going over to my solution for this, you see here's my little drawing, and Kirchoff's law says that applied voltage is equal to the sum of the voltage drop across the resistor and that output voltage, right? So here is a very good beginning of our equation. We have the input, E sub I, and we have E sub O. And so now all we have to do is get rid of current, get rid of I, right? Well, we know I is related to the voltage across the capacitor through these fundamental laws of how capacitors behave. And there's two ways to look at it, right? That output voltage is the integral of the current times 1 over C, or the derivative of the output is equal to 1 over C times I, or as we showed up in our table, the current through a capacitor is equal to C times the derivative of the voltage across it. So that's the one we want, right? We want to put that in to our equation we got from Kirchoff's voltage law, and we immediately jump right into a standard form of our first order differential equation with an input. So again, non-homogeneous. So that was kind of nice, and you'll see it's of exactly the same form of the mechanical system in the previous problem. The initial voltage is 5 volts. That means, as I mentioned before, the initial condition is 5, and at time t equals 0, E sub I goes to 10, right? So we have a particular solution. We have to, well, okay, this is the way we now write our differential equation. A non-homogeneous differential equation with an initial condition. We know the particular solution of EO is it's going to be just a constant because this input is just a constant, and it drops right out that A is actually equal to 10. So there's our particular solution. Our characteristic equation, RC d plus 1 equals 0. D is 1 over RC, and the homogeneous solution is of the form C1 times e to the minus t over RC. And remember, I just talked about that the coefficient of the exponential containing the time constant. Again, if you're familiar, if you remember to your original circuits course or maybe in physics, we talked about the RC time constant, which defines the way a system like this responds. So we apply the initial condition. Sorry about the messy stuff here, but we combine the two, C e to the minus t over RC plus 10. Remember, that's the particular solution. At time t equals 0, we get C1 plus 10 equals 5, so C1 is equal to minus 5. So that's our solution, minus 5 e to the minus t over RC plus 10. And I'm just remembering I gave you values for R and C, and if we go back over to our thing, so R and C is 10 times, R is 10 times 10 to the 6th, C is 0.4 times 10 to the minus 6th, so we have the two of those multiplied together comes to 4, and we get a time constant of 4, so it's t over 4 in our solution, which is exactly the same time constant we got from the mechanical system. So hopefully you got those answers, and you're starting to see kind of the consistency between the various types of systems, the various physical realms in which we'll be modeling.